Okay, everyone, it's 11:30 and I want to make sure that I finish this chapter for your quiz 4 and exam 4. And so, okay, I'm gonna get started. So, to save myself and yourself time and paper, what I did for the rest of the extra credits that I'm going to add to your exam 4 from now on, I just designed the extra questions in BBLearn as a multiple choice questions. And if you just listen to the lectures, you should be able to answer them well. So to demonstrate to you, I went to student preview in BBLearn to make sure everything is fine. So here you just go to extra credit and today's date. And then when you open that, it's as an exam format, but the questions are super easy if you just listen to the lecture today. And you just like choose the right answer, you know, based on the lecture, and then you progress to the next questions. There are 10 questions, you know, and then you answer them, and it gives you the final grade, which is this extra assignment is out of 10. But you have unlimited attempts. It doesn't give you the right answer because you easily with the notes and your book, you can find the right answer. But if you did the quiz and then you got like 6 out of 10, you can do it again. And the questions that I'm asking here and the extra assignments in general are really important because I'm going to use them to design your test. Does that make sense? Yes?
So if it's out of 10 questions, is it 10 points?
Yes, exactly. But unlike the other quizzes, or extra assignments rather, unlike other assignments that, you know, as long as you would do them, I would give you the credits, right? For this one, whatever grade you get here, you see the grade in BBLearn. But you have unlimited attempts. So even if you have questions, you know, you can just email me and I guide you how to solve it so you can easily get the 10 points. Are we good? Fair? Okay. So I start today's lecture by going back to some materials that we talked about before. Does any of you, I guess I just start with the shape of the orbitals and I just copy paste that page as you see from Google because I just wanted kind of to review the shape of the orbitals. Can anyone tell me, first of all, do you remember shells and soft shells? So what was shell telling me? What quantum number specifically? Do you remember? Where you want to, yes? What's that? Yes, but in general, when I talk about different shells, what do I mean? Like I say shell, the first shell, the second shell, how do we denote them? Exactly, with N, right? So n equals 1 is first shell, n equals 2 second shell, and so on. So what was subshell? What was subshell telling me? Do you remember? Exactly. So shell was telling me the first quantum number n, and subshell was telling me the shape, right? So here you see, like, for this S subshells, and I'm going to just, like, I guess circle it with like black here. So these are like S. This is S subshell or S orbital. And what is the shape? Exactly. And do you remember? So these are like my P orbitals or P subshell. What do they look like? Exactly. And for the rest, I'm not going to ask you the shapes, so don't worry about those. For the sphere and dumbbells, I'm going to ask you. But for the other ones, the important thing is to know that, 1, 2, 3, 4, 5. We have 5 orbitals when we're dealing with the subshell. Is that clear? And then for F, we have 1, 2, 3, 4, 5, 6, 7. So remember, S orbitals, they only have, or like S subshell, it has like only 1 orbital. But P subshells have like 3 orbitals, D have 5, and F 7. Is that clear? And then remember, S orbitals are sphere, the shape, and then the P orbitals are dumbbell-like. Okay. So, and I go back here, and here is kind of like, again, like your book didn't include the F orbital shapes. Here I just included them for you to see. And remember, 1, 2, 3, 4, 5, 6, 7. We have 7 orbitals. F subshell has 7 orbitals. So how many orbitals P subshell has? Do you remember P? 3, exactly. What was the shape? Exactly. So how many orbitals S subshell has? What is the shape? Exactly. Okay. So now that we're good with these, hopefully. Okay. So I'm going to give, and I'm going to post these in BBLearn too, so don't stress out about writing all of this. I just, will post these in BBLearn so you can just listen, because I have so many materials to go over in today's lecture. So I'm going to post this so you don't stress out about writing them. I will post them, and I will post the study guides for you. So now just listen, try to have all your attention to me when I'm talking about this. So can anyone tell me what was ground state energy? Yes? Yes, more of you say, all of you? Exactly. And as you remember, all the atoms, they prefer to go to their lowest energy state. So, and this is kind of how nature works. Atoms, molecules, they all form somehow that they have lowest energy possible. So know the definitions, because I'm going to ask you in the test. So the other one is electron spin. So in general, do you remember the orbital diagrams that we had? And we were like, if we had like, for instance, S orbitals, we were writing, or drawing arrows. So each of these arrows represent spin. And this is the definition of electron spin. In orbital diagrams, the direction of the arrow pointing up or pointing down represents electron spin. And this is a fundamental property of electrons. So your book doesn't want to go really deep into the equations or like really sophisticated, complicated things. So it just like gives you as little as possible to just solve the problems. So it doesn't give you more explanation. So for the purpose of this course, just remember that when you have like the orbital diagrams, you write arrows or you draw arrows, right? That they are better pointed up or down. So we call these arrows spin, which is a fundamental property of electrons. And this is the amount that I'm going to ask in the test. So don't stress about anything beyond this. And then we have two definitions, which definitely you're going to see that in the exam, one of these two. You already saw one of them in the quiz. So just remember, Pauli exclusion principle says that orbitals may hold no more than 2 electrons with opposing spins. What does it mean? So do you remember that we said one or like s orbitals? They, first of all, how many s orbitals do we have? 1, exactly. And this is how we write s orbitals in orbital diagram. And do you remember in the p subshell how many orbitals we have? Exactly, 3. And we write them like this. And then I mentioned this briefly at the last session before the break, but I didn't explain further. So this is how we demonstrate p orbitals. And then for D, do you remember how many configurations could we have for like D subshell? Exactly. Any question? Yes. Oh, okay. I thought you had a question. Yes, 5. Sorry. And it just goes automatically to eraser. Okay, 1, 2, 3, 4, 5. And this is D. And this is, I'm not going to, so just know that F subshell has like 7 orbitals, but I'm not going to ask you to draw them. So don't worry about them. This is the amount that I'm going to ask you. So Pauli exclusion principle, let's read it again. Orbitals may hold no more than 2 electrons with opposing spins. It means that in the s orbitals, I only can have 2 electrons. I cannot have 3. I cannot have 4 or 5, right? And the direction of the spins would be opposite. So the same thing with p orbitals. And since I'm going to first talk about Hund's rule and then have fill up the p orbitals. But is this clear, the Pauli exclusion principle? So in each orbital, we only can have 2 electrons with opposing spin. And as we said, if you have the arrow, pointing up, the spin is up. If it is pointing down, it is the spin is down. Any questions so far? Good? Okay, silence can be good or bad, whether it's not clear what I'm saying or everyone is understanding. I guess we'll know in the next thing that I'm going to write. So for the Hund's rule, when filling orbitals of equal energy, electrons fill them singly first with parallel spins. It means that when you want to fill p orbitals, first you put 1 electron here, then here, then here. And then go back and fill them up. Another one here, another one here, another one here. So the same for d orbitals. First, the electrons fill the orbitals singly first. It means that, and then with parallel spins. And then we fill the rest. Is that clear? So what this means is that, okay, I guess I just open another one. So if we have imagine this is a p orbital, right? So this is one of the questions that I'm going to give you in your exam on Friday. So which of the following can represent p orbitals in an atom? And then, the A, so I asked for p subshells or orbitals. So 1, and then I give you 3, or 4 rather. different options. So remember, p orbitals, or like p subshell has like 3 orbitals. It means that in the orbital diagram you have like 3 squares. So which of these ones okay, which of these are correct? Yes? Why? Why? Yes. So remember, when we have p subshell, when they are empty, all of them have equal energy. Okay? And when we want to fill them, first we fill them singly. It means that, and with parallel spins. So if I want to fill p orbitals, first, we fill them singly with parallel spins. It means that each square should have 1 electron and they should be parallel, like this. When you are done, you go fill them more, depending on how many electrons you have. Any questions?
Is that just for the p orbital?
No, this law or this states for all other orbitals too. So when you want to fill, for instance, so s orbitals are straightforward because you have to, it doesn't have multiple ones, so by nature you fill them like first one and then the other one. But you fill actually singly first and then pair them up. Is there any questions? Just ask me. As I said, we have so many materials to go through today, and that's why I didn't post a lecture online, because I thought not so many people listen to it. Yes?
So the top p orbital you drew outside of the A through D, would that also be a correct answer?
Yes, because you fill them singly first, and then you pair them up. If, however, it was a video, fortunately or unfortunately, we cannot implement like video to see how I fill them. But technically, if I would fill that like this, and then fill these two, it would be wrong. But as of what you see, it could have been right. So it depends on how you fill the orbitals. So the same thing for d orbitals. How many orbitals d subshell has? Yes. So we have like 1, 2, 3, 4, 5. So first you fill them singly and then put the rest. Depending on how many electrons your atom has, you may have like only, in the next examples that I'm going to give, it becomes more clear. But if your atom here, it has like only, in this subshell, it has only 6 electrons, you put like 1, 2, 3, 4, 5, 6. You don't need to put the rest. And remember, all of these arrows are electrons. And you can also put like the whole arrow, but you see that it would become so, it would be difficult to write all the arrows. That's why we write half arrows, but that doesn't matter. If you're more comfortable with the whole arrow, just write the whole arrow. So is this clear that what is like the Hund's rule? So can anyone tell me what is the Hund's rule? Do you guys want to say? What is the Hund's rule? Yes?
When filling orbitals of equal energy, electrons fill them singly first with parallel spins.
Exactly. So remember, I'm going to give true or false in the exam. When filling orbitals, electrons fill the orbitals singly first with unparalleled spins. True or false? False. Right? So just remember. And then, as I said, I'm going to give this in your exam, or really similar to this. So if you understand this, you get one of the questions in the exam. Okay? And the other one was Pauli exclusion principle that says orbitals may hold no more than 2 electrons with opposing spins. So another question that I will give you, whether in this exam or final exam, would be which one represents or is consistent with Pauli exclusion principle. I guess. Which one? Right? You can have like only two electrons maximum. You can have one, but the maximum is 2 electrons with opposing spins. And this is the same thing for like when you have like more orbitals too. You cannot have like this. For each orbital, you can have maximum 2 electrons with opposing spins. Good? Any questions? Okay. Now that we went through these definitions, I'm going to tell you some other information that I talked about briefly in the last session, but not completely. So I'm going to highlight this, I guess, maybe blue. So, we have like shell, and we have number of subshells. Do you remember that we had, like I told you, like for instance, when we have like, so number of subshells or like letters specifying subshells are like S, P, D, F, right? So in n equals 1, we only have one subshell, and that is like s orbitals. When n equals 2, we have 2 subshells, s and p. When n equals 3, we have 3 subshells. So basically, whatever the number of shell is, you have the same number of subshells. If n equals 3, you have 3 subshells. N equals 4, you have 4 subshells. And the letters specifying these subshells, or like these orbitals, but remember, each of these orbitals, for instance, p subshell, that's the reason we use like subshell and orbitals, because p subshell has 3 orbitals. D subshells has 10 orbitals. But regardless, if n equals 4, for instance, we have 4 subshells, which are S, P, D, F. And these are helpful when writing electronic configuration and orbital diagrams for different atoms, which is like the main purpose of this chapter. And here, if you have, for instance, S subshell, as we said, how many orbitals it has? 1, right? And remember, the number of orbitals is number of these squares that you draw in the orbital diagram. And P subshell has 3 orbitals. D subshell has 5 orbitals. F subshell has 7 orbitals. And do you remember that how many electrons can be in each orbital? Exactly. So the maximum number of electrons in s orbitals is how many? 2, right? Because based on Pauli exclusion principle, we can have only maximum 2 electrons with opposing spins, right? So what is the maximum number of electrons for p orbitals? Exactly. We can count these 2, like 1, 2, 3, 4, 5, 6. What about d orbitals? What is the maximum number of electrons? Exactly. What about f orbitals? Exactly. Is that clear? Any questions? So if I ask you in the exam, is the following statement true or false? An atom can have maximum 14 electrons in its d orbitals. Why? Exactly. Or I say that the maximum number of electrons in s orbitals are 6. True or false? Why? What's that? Exactly. So are these making sense? So can anyone tell me what are these arrows specify? What are these? Exactly. So I give you the arrows in orbital diagrams represent protons. Is this correct or false? Exactly. So remember, these orbital diagrams, electronic configuration, all of these things represent electrons. These arrows are electrons, and as your friend says, electron spin, because if it's up, the spin is up. If it's down, spin is down. Any questions? Okay. So let me go to another fun slide. So now we want to start writing electronic configurations for different atoms. And as you may guess, based on the ground state and everything that we talked about, we feel the orbitals depending on the amount of energy that those orbitals have. So we have two things here. We have energy, and I think I highlight them with blue, I guess. Okay, so we have like the energy diagram here, right? And you see that 1s orbitals have the lowest energy. Okay? And then 2s. And then as we go up, the energies increase. And then do you remember that in Bohr's model, we said that when we go from the first orbit or first shell to the other, energy increases or decreases? What's that? So when we had like, let me draw here. So you had like nucleus here, and then you had like the, this is like n equals 1, and then you had like n equals 2, and then you had like n equals 3, and so on and so forth. And then we said like this orbit compared to this one has higher energy. Do you remember? So n equals 2 has higher energy than n equals 1. And then we kind of explained that as the fact that when you have your nucleus and then you have like a shell right after, the shell has positive charge. And the electrons have negative charge. So if you're in n equals 1, nucleus has lots of control on n equals 1. And do you remember that positive and negative charges attract each other, right? Do you remember? So for that matter, that electron cannot move freely. It has like more restriction compared to n equals 2. So as n increases, if n equals to infinity, imagine that I'm nucleus and I have positive charge, and there is a negative electron at the back of the class, right? So I don't have any control over that electron. The electron can freely move, so it has lots of energy. So if you just remember this example in your test, you remember that, okay, n equals 5 is further from the nucleus, so has higher energy. Does that make sense? Okay, so this law, what I just talked about in Bohr's model, kind of stands here too, but not completely. Because as we talked about, Bohr's model has flaws associated with it. And we don't only have orbits, we only have orbitals. So in general, you see that, 5s, oops, wrong pen. Okay, cool. I go to my highlighter again. Here, 5s has higher energy than 4s, than 3s, 2s, 1s. So Bohr's model stands in some level. But here you see that we have like, different orbitals. And 2p2, we have like, as you remember, we had like 3 different directions, 2px, 2py, 2pz. Just know that we have 3p orbitals. And then here we have like 3p's and then 3d's. So you see that 3d has higher energy than 4, although the orbits, or like the principal quantum number n, is higher in 4. We expect it has higher energy, right? But 4s has lower energy than 3d. So this is where Bohr model failed, as we talked about, because we only don't deal with orbits, we also have orbitals. Does that make sense? So as long as you know that how these energies are, and I'm going to tell you here orbital filling order. I'm not going to ask you all of this to remember, but just remember, the thing that I expect you to know is that 1s has the lowest energy, then is 2s, then is 2p, then 3s, 3p, then 4s, and then 3d. Just memorize this. And based on the Bohr model, you should have an idea, but based on quantum mechanical model, you should know the exact energy. So 1s, 2s, 2p. Can anyone tell me why didn't I write 2d? Can anyone tell me? What's that? Exactly. So we have like, you remember that, and then I said n equals 2, we have 2 subshells. SP, right? When I say n equals 3, is it 3? I have 3 subshells, SPD, right? So here you know that when you write 1s, you know 1, n equals 1, has 1 subshell, that is s. And then n equals 2 has 2 subshells, SP. And then n equals 3 has 3 subshells, SPD. But here you have an exception that you first fill out for S, then 3D, because that has lower energy compared to 3D. So we fill orbitals based on their energies. First, we fill the ones that have lower energy. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. And this is till here. I'm going to ask you in the exam. So anything that I ask you to write the electronic configuration for would be up to 3D here. So you don't have to stress about all of this, but I wanted you to see that how their energies are. But I expect you to know up to here. Does that make sense? The things that I'm saying? Just remember, different orbitals have different energies. 1s has lowest energy, and then 2s, 2p, just what I wrote. Yes?
How do we know, like, with 6s, that there's only going to be 3 instead of 4?
What is the question again?
For, like, the 6s and then 6p and then 6dy, why is it there like a 6s?
Oh, here. You're asking here?
Yeah.
So this is the order that we fill the orbitals. So first we fill 1s, and then you can follow this arrow. This is like your figure 924 from the book. So first you have 1s, 2s, 2p, 3s, 3p, 4s, and you just continue that. And you fill orbitals based on these patterns because they have based on their energy levels. And you're asking, how do we know the energy levels? Is that the question? I'm not sure what exactly is your question.
How do we know, so does like, does six, is there a six F, but it just is very, it's really high energy, so it's not put up there? Or is there no six F?
So theoretically, these numbers can go till infinity, but in your periodic table, you have like up to 118 electrons. Does that make sense? So we end this at some point. But theoretically, if an atom lost an electron, it goes to the orbit of n equals infinity, if that makes sense. But as I said, in the course that we're having now and in the exams that you're taking, I'm just going to ask you till 3D. But I expect you guys to know it well because I'm trying to explain it well to the best of my abilities. And if I'm not, just ask me and I try to paraphrase or like explain further, or just come to my office hours, or just like email me and I just like schedule Zoom meetings for you. I try to accommodate all of you. So, any other questions? Are we good? Okay, and here I wrote how we actually fill them with electrons. So, as we said, s orbitals can have like up to 2 electrons, and then p orbitals 6 here, as you see, and then d orbitals 10. So when you want to write the electronic configurations, if you just memorize this pattern, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And it's, as I said, it's not hard to memorize this because 1s has 2 electrons. And then n equals 2, or shell n equals 2, can have like 2 subshells, s and p. And then you write 2s2, 2p6. Does that make sense what I'm saying? So if you just remember these numbers based on the number of electrons that you see, or like the element that you see in the exam, you can just choose the right amount of or number of electrons and answer the question easily. If you just like remember this. And as I said, you don't even have to memorize this. Just remember you have an exception here between S and D. Okay, any questions before I go to the next slide in a sense? Okay, so now I wrote here some examples, right? We just study these so we can actually solve problems, right? So here, write electronic configurations for each element. So for instance, magnesium. So the first thing you do in the exam, and I'm going to give you your periodic table, don't worry about it. The first thing you do, you go to the periodic table and you read the atomic number. Remember, in some of the problems, in most of the problems so far, you were reading the atomic mass unit, or like molar mass, which is the number below the element that has decimal points. But here, you read the number above. And as you remember, I told you an example about like atomic number is number of protons, which is also the number of electrons, because each element as it is neutral, right? So number of electrons equals number of protons. And it cannot have decimal points because this is a number. As we said, we don't have like 2.5 students. It's just whether 2 or 3, right? So remember, this is the first thing to know. And then, based on this pattern that I told you, when you want to write electronic configuration, one way is to just remember what I told you, that you can just write, 1s2, 2s2, 2p6, 3s2, remember? And then count the number of electrons. So here, I'm just going to write it as it is for magnesium. So 12 electrons. What is the first orbital that I'm writing? Exactly. And how many electrons it can has? What is the next one? How many electrons? What is the next one? How many electrons? What is the next one? How many electrons? So why didn't I write 3s3? What's that? Exactly. This is the maximum number. And here you count, as you write this, here we have 2 electrons. And then 2 more electrons. And then 6 electrons. So far we have 10 electrons here, but we have 12 electrons. So I should add 2 more. So I also write 3s2. Is that clear how we write this? Any questions? Okay, so now if we want to write it for neon, again, you go to the periodic table, find the atomic number, which is number of protons, which is also the number of electrons. And then you write 1s2, 2s2, and then you count. So far I have 4 electrons. Okay, I should continue, 2p6. Now I have 10 electrons in general, right? So let's do for manganese. We have like 25. So I say 1s2, 2s2, 2p6. Then I take a breath, add electrons. Here, so far I have 10. I still should write more. What is after 2p? What is it? So here I have 12 electrons. What is it after 3s? Is it 4s or 3p? Right? So I have 18 here. So what is after 3p? Why is it not 3d? Shouldn't we feel first n equals 3? So that was the exception, remember? Although we have like, in n equals 3, we have 3 subshells, S, P, D, but 4s has lower energy than 3d. So we first feel that one, right? So here is 20, and here 3d. And now we count this, like here is like 10, 12, 16, or 18, 20, and then it should be 5 here, right? Does that make sense? And then for argon, it has like 18 electrons. We write 1s2, 2s2, 2p6, 3s2, 3p6. And one thing that your book does and all other scientists or chemists do is that in order to prevent writing all of these, they write each of the previous. So here, if you notice, when I write magnesium, let me write it with red here. We have like neon here, the noble gas, before magnesium that has like till here. So some people, what they do is that they write neon 3s2. So in order to write the electronic configuration, they represent it by the noble gas before the element to save time and space. Or here, for manganese, here you have up to 3p6. So you write that as argon 4s2, 3d5. So you represent each element with the noble gas before it. Does that make sense? No? So you see that here, is it clear for each of them how we wrote the electronic configuration for like magnesium or like neon for each of these. So sometimes like here, especially for, when the number of n increases, it's difficult, to write all of these. So we kind of, here, as you see, up to 4s, or I guess up to 3p6. Up to here, 3p6. This is the electronic configuration of argon, right? So here I write up to here as argon, and then add the rest. Kind of like to save time and space, I guess. Any more questions? When you guys talk, I don't know whether it's a good sign or a bad sign, whether you know the materials well and it's boring, or you don't know and you don't care. So hopefully you know them well. Okay. Now I'm going to talk about some definitions and some trends. Okay. So the first one is valence electrons. And as I said, I'm going to post this in BBLearn or like in the website, but make announcements. So don't worry about writing this. Just listen to me. Valence electrons are the electrons in the outmost principal shell. So here, for instance, in magnesium, when you have like here 3s2, the outermost shell is 3, n equals 3. The number of electrons is valence electrons, or those electrons are valence electrons. Or here for like sodium, again we have like 3s1, right? N equals 3. In the outermost layer, which is n equals 3, we have 1 electron. So this is valence electrons. And these are really important because these participate in chemical bonding, reactions, and so on and so forth. So these are really important. And we have something named atomic size. The atomic size of an atom is determined by the distance between the outermost electrons and the nucleus. So here, the distance between the nucleus and outermost electron. This distance is atomic size. So these are definitions, just remember them. And now, in a periodic table, when, here, when we move in a period or in a row, for instance here, going from like sodium to magnesium, here, and I wrote down the, Bohr model and kind of electrons, and asked me if you have any questions now or after the class. So here we have like 1 electron in the outermost layer. Here we have 2. So when we move in a row, as we go from left of the periodic table to the right, atomic size decreases. And you can kind of imagine or like consider the example that I gave before. Here, the nucleus has more control over like these 2 electrons here, this one and this one. And because they have like negative charge, nucleus has positive charge, they kind of like, they are less restricted, so kind of like the atomic size decreases. But here, this one, it has more energy, so it can move more freely, so the atom is bigger. And I asked you this in the extra point questions and also the quiz. And when you move in the periodic table from up to the bottom, you have 1 more layer, and atomic size again increases. And you have some more definitions, which I'm going to post, and I encourage you to study, and I have 3 more minutes, so don't rush. I'm trying to finish this. Ionization energy. Ionization energy of an atom is the energy required to remove an electron from the atom in the gaseous state. And here is the definition. And metallic character. Metals tend to lose electrons in their chemical reactions. Remember, they have positive charges. While non-metal tends to gain electrons, they have negative charges. As we move across the periodic period in the periodic table, ionization energy increases, which means that electrons are less likely to be lost in the chemical reactions. So to recap what I just said, let me here, atomic sizes. You know, when you go from left to right, as you can see here, atomic sizes decreases, but in a group, when you go from up to down, you know, so from left to right, atomic size decreases, from up to down, atomic size increases. And also for the ionization energy, you know, when you go from up to down, ionization energy increases, and from left to right also increases. And this is the same trend, or kind of like similar, with the metallic character. You know that these elements here, these are metals, here are non-metals. So when we go left to right, metallic character decreases, and up to down, metallic character also increases. And you can remember here, you have like, you know, metalloids here, which are kind of, you know, have metallic characteristics, but here you don't have them. Okay. Just email me if you have any questions, and don't forget about the extra point credits. There are like 10 free points. Yes. Yeah, of course.